The first speaker is Lincoln Carr, and Lincoln was a I'll say this, was a graduate student of Bill Reinhardt, who's a very old friend of mine. Some of you people might know Bill. He did a lot of stuff in scattering theory for many years and had many good students.
That's our connection.
Rick Heller was one, Tom Machino was one. So you have a nice long lineage of good people. And he's going to talk about quantum simulator packages.
Okay.
Be my guest.
It's a pleasure to be here at ITAMP in Harvard. I'd like to talk with you about the package that my group has put together. This is about 12 years of development. It does lots of things. And I'm first going to describe what we did, how it connects to what a lot of people in this audience are doing with molecules and atoms. And then I'll talk about some of the different platforms out there that we started to engage with and where we might build together toward any kind of collective software effort. Okay. And I wrote this talk, as Barry asked, mainly in response to what's been discussed at this meeting. So intentionally, it's mostly about what's been happening here. So I hope it'll be relevant to you all. I should mention that, I interact with all kinds of organizations around this, but I mean that the major funding source is NSF, and I don't just say that because Mike's in the audience. It also happens to actually be true. But I'm very grateful to have lots of great colleagues to these different organizations. So you may have seen this rather little-known paper from Google, which claimed that if you only had 40-something qubits, you could rule the world. Talked about Google's idea of so-called quantum supremacy. We can politely call it quantum advantage. That's all very nice. This paper came out in 2016 and said one day we might do this, but guess what? Actually, we've had this since 2003, demonstrably so, in quantum simulators. Specifically, here's a couple of problems that since 2003 we've solved with quantum simulators that before that we really couldn't solve on a classical computer. And so one of them is the question of strongly correlated quantum fluids, or how do fermions become bosons. And halfway between fermions and bosons you get what's called a unitary gas. I was at the many-body meeting in 1999 where the theorists using the latest and best numerical methods, at that time quantum Monte Carlo, tried to predict what would happen and thought this thing would implode. So that was absolutely wrong. Okay, so that's an example, right? And this connects to great physics in quark-gluon plasmas and now through holographic duality, and it really goes very far. It's an example of what quantum simulators can do for us. And a second concrete example is atom interferometry in the experiments of Jörg Schmiedemeyer, where he takes a BEC in a tube-like configuration, splits it in two, and then recombines, and then does this interferometric measurement, and he can get up to 10th order phase correlators. So to give you a sense of how big a deal this is, when I teach the theory of quantum phase transitions, I'm always talking about second order correlations because that's what you measure out in experiments, and that's what tells you about quantum phase transitions, coherence lengths, off diagonal long range order, etc. For 10th order, we don't even know what those correlators will do. That's so far past anything we've ever done on any computer. And none of my codes can get 10th order correlators. Maybe there's complex network structure in this system. I'm working with Jörg now to try to understand that. Okay, so there are over 300 experimental systems on about 10 platforms. Ones you may be familiar with that are particularly relevant to AMO or ultracold atoms and molecules I'll talk about today. Trapped ions I'm also modeling and also for Rydberg gases. There are superconducting Josephson junction-based nanoelectromechanical circuits. That actually involves lots of different platforms, but they're all sort of dilution fridge-based. There are exciton polariton systems, and there are many others, including quantum optical systems. So I want to give you a sense that this is a robust field. It's not a field that's 10 years off. It's not about if we had 50 qubits, we could do these things. We've been doing them for 15 years, and they've had tremendous physics impact already. Okay, that's just two of many examples. So I'm going to choose a particular case study to start out this discussion, and that is something I've worked on a lot personally and is relevant to people here, and I think you will see why having more than one code talking to each other in the same kind of environment could really, really help our work. Okay, and so that's the question of ultracold molecules in optical lattices, or a crystal of light. So here's an electric field. Here are my little diatomic molecules. They're supposed to be rolling around some kind of lattice made by these interfering laser beams. So this is an intersection of molecular structure. You have to understand molecular structure very well. That is hard and needs code and is far beyond many of the things that I do. And then you have to do entangled many-body physics, which is hard and also needs code. So you have two kinds of code, at least, that have to talk to each other. Okay? Now, ultracold molecules, unlike a lot of these quantum simulators, are uniquely suited to study the questions of open quantum systems. That's the quantum measurement problem, right? And that is a very significant problem that is still not resolved today. And so to give you a simple concrete example, if you start with two diatomic molecules in crossed electric and magnetic fields, And for the case of this example, I'll just use potassium rubidium, which was already done at JILA 10 years ago. You see that there's some kind of nuclear spins here, and then there's the ball and stick model of the molecule, right? Okay, and so now, by the electric field is on to create the dipole for these molecules. Is the right-hand rule bothering you in some fashion? These fields don't have to be at 90 degrees. Okay, so so if we use the AC microwave field to cause one rotational transition, right, and from n equals 0 to n equals 1, then we get out 4 internal rotational states, right? And then in each molecule, there's the nuclear spin. So from nuclear hyperfine degrees of freedom, we end up with 36 states. Okay, and 4 times 36 gives you 144 internal states. That is not a qubit. That is a qubit with a very big D. Okay, it's a controllable quantum subsystem. Now, why is that a open quantum system environment? Because you can cause just 2 of the states to couple to just 2 of the other states, and then you get a quantum Ising model, right? It's a long-range quantum Ising model, but you have a tunable spin reservoir. Now you can control everything that you can't control in Libblad master equation. Okay, so that's exactly why that happens. And that area is so exciting that we have an entire program running at KITP, which is oversubscribed by a factor of 3. I'm not kidding. So please don't hate me if any of you applied and I wasn't able to get you through. I mean, it's almost an impossible situation. I think within 3 days we had 72 applicants. Because these quantum simulators present an opportunity to explore open quantum systems in a way that we just can't do on classical computers. Okay, so I hope that motivates things a little bit. Okay, so what is the hardware of these quantum simulators? The hardware of the quantum simulators is a lot of what's been talked about in this meeting, right? It's, for example, the internal structure of these molecules. And you can go through different kinds of molecules from singlet sigma to doublet sigma to, for example, neutral OH to things like methyl fluoride, you know, and symmetric top molecules. And you'll find that you get more and more internal degrees of freedom. Is Hussein here? Is he sitting back? There we go. At some point, when I was presenting this sort of thing a few years ago, we talked about OH, and Hussein said, isn't that a 2-state system? You know, because at high temperatures it is, right? It's lambda doubling, it's 2 states. You can think of it as a sort of a qubit, right? But at the kinds of temperatures in quantum simulators, that's a 16-state system. Before you even dress the states, it's a pretty big qubit, right? So we had this nice conversation, and that helped me understand, you know, why this is a really different regime of chemistry. So the hardware involves quite a bit of software, actually, understanding the hardware. Okay. Now, what about the software of these machines, right? On these machines, we run entangled many-body physics. And as I just mentioned with the open quantum system problem, a lot of times we actually can't run that at all in a classical computer. But we can get some pieces for design protocols on classical computers. So, for example, for statics, you've probably heard about Hubbard model and high TC, but that's really just the beginning, right? That's pretty well fleshed out now, I think. But there are many well-known spin models you can run, like quantum Ising and XXC. And even though you think, oh, those are integrable models, once you start doing interesting dynamics or ask questions about thermalization or ask how that happens in the context of different kinds of reservoirs, the sky's the limit. Actually, that's not in textbooks at all. Okay? And then exotic spin models like XYZ and beyond can also be done. Okay? And then if you want to do dynamics, you can ask things like, well, what about, I don't know, Kipple-Zurich scaling? So that's like the density of defects when you go through a phase transition, depending on how fast you go through, depends on the ramp rate, and it's trying to define non-equilibrium physics out of equilibrium physics. Sometimes it works, sometimes it doesn't. What happens if you have long-range interactions in that problem? That's something I could address with this software. Okay? And then you can go much further than this and get into things like quantum complexity, where you've got hierarchies of scale and emergent phenomena. For example, you can take those molecules I just showed you and use that to design new materials like a lattice of molecular magnets. All of that is well beyond what's done right now in condensed matter physics or solid state physics. And you can do things like run quantum cellular automata and ask about origins of complexity. Okay, so what do the models look like? What does the software look like that I'm trying to understand? Okay, so here's an example for the molecular Hubbard Hamiltonian. It shows you how hard this problem is. Okay, so first of all, you have some detuning between the different internal states sigma, where those may stand for rotational and hyperfine states. Then you have the spatial hopping, and the hopping may depend very much on those internal states. If something's rotating very fast, it's going to move differently through an optical lattice than if it's not rotating at all. Right, because of AC-Stark effect. Okay, and then you have different kinds of interactions in a magnetism. These correspond to direct and exchange interactions. Exchange interactions cause sort of spin flips at a distance. and direct interactions are, sort of density-dependent interactions. And then finally, you typically have some kind of internal drive, which you may or may not remove through some sort of rotating wave approximation. Okay.
So, sorry, a particle is the molecule or an excitation?
A particle is a molecule on site I, and then with internal state sigma. So those would be all the quantum states. Those are the single particle modes.
More than one molecule?
This is a many molecule problem, absolutely. So just that piece, just getting that piece correct already involves a lot of major code that was discussed over the last few days that I don't even understand that well, but I'd like to be able to use better without having to become a chemist at the level of Roman, for example. I mean, this is, many years of work to get to this level. On the other hand, just this lattice piece is another significant piece, and that's before you model all of this. So I'll show you some more details with some real numbers to give you an idea of how these different pieces of the software talking to each other could really create something wonderful. So here's something that I typically get from physical chemists. This is a table of numbers from Jeremy Hudson and collaborators in the UK. I'm part of their Quantum Science with Ultracold Molecules grant. And so I cannot a few of these numbers I can guess at, like rotational constants, but basically many of them, particularly like the nuclear quadrupole moments, I mean, I have no way to figure those out ahead of time, and I don't know how to use your code in a push-button way. I could grab some code open source from somewhere, but I wouldn't know how to use it properly, right? Okay. So, for example, if I'm talking about potassium, rubidium, cesium, and lithium cesium, those are three diatomic molecules that are singlet sigma molecules. They're very simple molecules compared to what a lot of you guys do. And already, look how different these nuclear quadrupole moments are. Extremely different by orders of magnitude by sign. Now, that is a key term in the emergent many-body physics out of the system. If I don't understand that piece of the hardware, I don't understand the software. Okay, even after I have the single molecule constants that go into this problem, I then have to put them in the lattice, right, go into some Wannier basis and figure out all of the lattice constants. I know it's awful to show tables of numbers, but because this is a group of computational scientists, I thought you might like to see a lot of numbers. So I hope you don't mind that I put these up. Okay, so things like tunneling, which are about, motion through the lattice, I can guess that I can guess that maybe for KRB that tunneling is going to be a lot faster than for rubidium cesium because rubidium cesium is heavier, right? It's going to tunnel slower. So that's something I could guess at. But other things like how different the direct dipole-dipole interaction will be, by 3 orders of magnitude for those 3 molecules compared to, say, the exchange dipole-dipole interaction, right? That is not something I can get without knowing a lot of molecular physics. Okay, so one piece of code, second major piece of code, and then finally I get out a model, okay, and the model has lots of different regimes. So here's an example where I'm able to reproduce things that are seen in simple scalar systems without internal degrees of freedom. Already you have superfluid, supersolid, and crystalline phases, right? If you turn up the B field and split out a lot of states and connect just 2 of them, depending on how you connect them and which molecule it is, you can either get XXE models or you can get more kind of XY type physics, okay? So depending on whether direct or exchange term dominates, you get Ising-like or XY-like type physics. And then finally, if you turn on lots of internal states, we actually have a general field regime, which is a quantum complexity problem and represents this tunable open quantum system, right? So all of those things can be run out of this hardware, but you have to understand the hardware first. And then if I want to model the hardware, right, I can run my code, and these are the kinds of things that I can get. I can treat 1D chains of molecules. These might be 20 to 100 molecules with a few internal states. And here's an example of lithium cesium, sodium potassium, rubidium cesium, all out of experiments. What I'm showing is as a function of electric field and chemical potential, I can tune through a phase transition indicated by this dashed line. Inside of here, I have a Mott insulator, and outside, I have something that's much more superfluid, okay? For the same molecule, I may have a period like a Mott insulator that's every site, or I may have a Mott insulator that's every second or every third site because of dipole-dipole interactions. So the results of QuSP are very rich already, but involve that underpinning that I showed you of those 2 other codes. Now, here's a piece of the molecular physics that comes in that I could not get had I not been interacting with Jeremy Hudson, who then spent many years, getting all of those constants correct, right? And that's the fact that this nuclear quadrupole moment, as I mentioned, is really key to getting out the molecular physics. It mixes the rotational and the hyperfine spin projections, right? Because one part comes from electric field and one part from magnetic field, and it's a nuclear quadrupole moment that would cause those to couple, right? Because it's the gradient of the electric field over the nucleus from the whole molecule, so that's electric somehow, yeah? And then the nuclear piece is magnetic, right? So if the 2 of them couple, depending on the relative angle of the external electromagnetic field, I get totally different dipole-dipole matrix elements. So there's another piece that requires significant code to calculate. Okay, So this is this sort of tunable complexity idea. And then the emergent many-body physics out of that is extremely different, right? You have just a couple of states interacting, you have all of the internal states interacting. Okay, and here's a kind of practical prediction you could make, just the last slide on molecules here. So, you know, if you choose a very fast Rabi frequency, you can decouple the single and the many molecule physics, couple just two states, you get Rabi flopping. If instead, you know, you go into a different regime where the single and the many molecule physics are coupled, then these internal states start to affect this problem. You see some interference, and over long times you get quantum dephasing or some kind of damping, right? And this is observed at JILA, okay, for KRB. So now you see this whole process. There's a lot of pieces to the code, right? It's single molecule physics, and then it's the lattice physics, and then it's exploring the different regimes, and then it's talking to the experimentalists. And even what we did here, we only ever did a 1D system, but in the JILA experiment, it's a 3D lattice, right? Which we cannot model. We cannot get to that on a classical computer. So a lot of pieces go in. Okay, so what is QuSP? We're computational scientists, and let's talk about what QuSP really does. It is a classical software used to model quantum software. That is what it is. Okay? Why does it save over $1 million? Because building quantum software means building quantum hardware means a lot of money. And if you build out the wrong thing, you've now built a toaster when you need a blender. Try taking apart your toaster and making it into a blender. It's a long process, right? So that's why this kind of software is very important. Okay, it does statics and dynamics in 1D spin chains. For example, it does matrix product state methods like TBD, DMRG, etc. It does exact diagonalization, which means I may, for example, use trotterization in time. It treats both closed and open quantum systems now, so it'll allow you to do Lindblad master equation and beyond. It allows you to do matrix product density operators, quantum trajectories, and lots of perturbations on those methods. Physically, what can you get to? Certainly you can change statistics from fermions to bosons or anything in between. You can treat different geometries like periodic boundary conditions or kind of nanoribbons, you know, like a multi-legged ladders. You can treat shorter or long-range models. It gives you access to Ising, Hubbard, Heisenberg, XYZ, quantum Cellular automata, a long list of different models you could do. And as I mentioned, nanoribbons, but also things like disorder or scattering, or if you want to explore devices like a quantum coherent FET, you can do all of that with this code. It's a very powerful code. Okay. It's a standalone code. It's easy to download. It compiles in a few minutes. I just tested it again last night to be sure, and I even did it in Windows through VMware, or it was actually VirtualBox, which is really has bad overhead on it, right? And it worked just fine. Okay. There's so it's. Let me get to this now, and I'll explain that. So there's a large help manual with lots of examples. There's different models of containerization. So it was originally a Fortran code, which, by the way, Barry had some hand in some very early version of it, some small piece via a colleague of ours, Jamie Williams. So we started this effort a little bit at NIST, and then eventually it left NIST, and my group, you know, took it and turned it into something gigantic, and now it does many things. But on the TBD piece, you actually had some hand. Your name somewhere is in, I think, version 1.
I simply figured out how to write a time-dependent exponential and give it to you.
Yeah, there we go. Barry's still writing code. Okay, so as far as containerization, to answer that was Roman that asked that, right? Where are you? Yeah. So as far as containerization, originally it was designed to be sort of a Linux-oriented code. It was pure Fortran. And then we put a Python wrapper on it. We already had a wrapper concept before, but the Python wrapper is a lot easier to use. And then we tweaked it to run on Mac and Windows and virtual machines. And what we're doing now, we haven't yet released to the website, and I've got an example here I can show you, but we run it through Docker with Jupyter notebooks. We're writing a GUI. It's going to have a science gateway, and we have a prototype for this, and it has a model store, you know, where whatever model you want, you know, you just get it from a pull-down menu. There really isn't any coding. It's all graphical. So that's sort of where we're going. But as far as the Linux-oriented Python wrapper stuff, that's been around, I think, since 2014. And in its present version since 2016. So it's pretty well established. Okay, so that's what the code does. So QuSP is in the computational literature. Klaus very patiently suffered through our insanely long paper on a set of methods called matrix product state methods, and this is in CPC. He was very generous about all this. We have a couple of preprints up if you're interested on the exact diagonalization and ideas and why that's a lot more than you think it is when it comes to quantum many-body systems, and then also on doing open quantum systems properly with lots of examples like exciton transport, Bose-Hubbard dynamics, etc. So there's a number of papers you can find in the archive on this topic. Okay, now, QuSP has lots of physical outcomes, and I'm just going to show you 3 slides of physical outcomes, and then we're going to go back to talking about code. But I feel very uncomfortable showing code without showing you the physics it produces, okay? So here's one set of very concrete predictions. What happens to the Ising model when you have long-range interactions? So that is in trapped ions, that is in Rydberg atoms, that is in molecules. All of the quantum simulators have this effect, actually, that I know of right now. So here's quantum Ising model. It's a ZZ interaction, right? Coupling, and then some transverse field, and then there's some power law on the bottom, and that power law on the bottom modifies the usual Ising model dynamics. So as you may recall, it can be ferromagnetic or antiferromagnetic depending on the sign of this guy out front, J. And then what you'll find out is that as you play with this power law exponent, as it gets stronger and stronger, you deviate one way for antiferromagnetic and the other way for ferromagnetic, okay? And now you can ask yourself, like, is that phase stabilized somehow? Does the presence of long-range interaction somehow prevent defects from forming as you go through a phase transition? Okay, so if you go through a phase transition, which means I ramp the transverse field H in some very simple, naive way, then I'll find out that the density of resultant defects rho is proportional to the ramp time to the power minus mu, where minus mu is called this critical exponent, Kibble-Zerk exponent. Okay, and so what you can see is that, you know, in the antiferromagnetic case, there's almost no change as a function of power law, whereas in the ferromagnetic case, there's actually quite a big change. Okay. And I could go into, you know, the physical reasons why that is, but I want to point out that that's now being tested in a number of quantum simulator experiments. That's a very concrete thing. I ramp through a phase transition. I want to know if I have defects. You can see the defects. So this is an example of you know, something that really matters for quantum simulators. One more. Yes, is there a question? Those are simulation error bars, and they come from a number of factors, but one of the key factors is simply the Schmidt number in the calculation, right? And how well converged that is. But there are many other things that actually, DMRG methods have actually a number of convergence criteria in them. It's not just so-called Schmidt number truncation. That's just the dominant one. There's also the tritorization. But on top of that, actually, there are a number of other criteria that come in, which I would like to talk about at the end, as they're a bit technical, if that's okay, having to do with accuracy as you go through a sweep. Okay, so in any case, so, you know, very definite, concrete predictions. I think people were asking about accuracy. I do have error bars, real error bars in the paper. They're done in great detail. In fact, I made my student delay a year to get those error bars, by the way. Okay, so another example is to find something new in quantum states, which is complex network structure. And so complex network structure, I like to say, is the Facebookness of a problem, right? Is the friend of your friend, is the friend of your friend also your friend or not? You know, that would be an example. That's called clustering. And so what happens is you find this community formation in complex networks. So without going into too much detail, it turns out that, for example, for the Ising model around G equals 1, then there's some kind of interesting external behavior in all kinds of complex network measures. Okay, and same for the Bose-Hubbard model as you go through so-called BKT transition at the tip of the Mott lobe. So the point is, at quantum critical points, there's some interesting complex network structure, and that's not something we could have really gotten to ever, pen and paper. And it's actually quite hard to pull out of experiments. So in that sense, you know, this has been predicted toward experiments. Now experimentalists want to measure this. Okay, and then you can take that and use that to direct non-equilibrium studies like quantum cellular automata. And quantum cellular automata, remind you, are just, you know, rules where you do something depending on the state of your neighbors. So in this case, I'm looking both right and left, not only to one side, but to both sides on a lattice. And I do something if the neighbors have some certain spin states. And so depending on the rule set you use, you'll find out that sometimes, for example, for this rule 6, you get this very intermediate values of complex network structure. That's in common with quantum critical points. And then if you drill down and you look at what's happening here dynamically, it's something very different. It's not an integrable model, but it's not thermalizing. So there's like some very new physics there. So people have gotten excited about this. Okay, enough of the predictions out of QuSP. Our own PRLs out of QuSP in the last year or so have covered things from practical things from quantum tunneling to quantifying complexity to things like, you know, new regimes of many-body chaos, which are really quantum entangled in nature. Okay. If you want to know who's actually using this code, we've had about 3,000 downloads. Here's the sort of stats. It's running through SourceForge at the moment. Actually, the code is much older than this. This is just when we first posted it on SourceForge. And some people don't get it through SourceForge. We also have a GitHub copy and everything. So this is a sort of a lower bound on the users, but at least gives you an idea. Okay, so it sounds like I'm saying, wow, QuSP is amazing. You can do everything with it. But the main point of my talk is that actually QuSP is very limited. And it's limited because there's this terrible bottleneck, which I myself have experienced over and over in my group. And the bottleneck is that QuSP requires input from your codes, right? I can't do anything with the software if I don't know about the hardware, the quantum hardware, okay? So for example, if I want to study the many-body entangled dynamics of ultracold molecules, right, I need to know the molecular parameters. And right now I'm outsourcing that to, like, you know, a group in the world that has an expert who does this, you know, as his full-time thing, basically. Okay, it's really actually 3 people doing that. And then molecular spectroscopy, you know, I tried to do this within my own group, and each of those projects is an entire year of work because I don't properly know how to use your codes. I have to go and rederive all this stuff from Brown and Carrington and then write it all up in code, yada, yada, right? I don't have a good app store to just do that. And then I have to get the molecular Hubbard parameters, which is a whole other piece. And I want to know, for example, if I'm modeling magnetism, do I have exchange or direct dominated magnetism? Very basic many-body question. I cannot do that without these other pieces, okay? So there's really no one code space or resource for quantum simulators. Okay, the best out there is modeling code for quantum computers, right? Like what Google has. There's some very nice codes out there, like QTIP, as we mentioned earlier in the program, but there really isn't something for quantum simulators, and yet we have over 300 experimental platforms. It's pretty amazing, right? So QuSP really goes nowhere without understanding the hardware, okay? So how can we solve this? So in the rest of this talk, I'm just going to talk about existing resources and support out there. The rest of this talk is very much built on the conversation over the last few days. I'm not going to suggest any one solution. I'm just going to present some possibilities, okay? So can I have another 5 minutes or so? I don't know where I am on time. Is this okay? Okay. So I came out of this ALPS project, which I mentioned to you guys, and you know, ALPS really did something very well, which is that it had these developer workshops where it would take students and postdocs and train them in how to use 8 or 10 different codes at once, not just one code. So students who came into that would know quantum Monte Carlo, they would know matrix product state methods, they would know exact diagonalization, and they had a package which, although unwieldy for people who did not go to the programs, nevertheless for those people who were in the programs was incredibly useful. So for example, my student Ryan Mishmash, who went to this, went off and did absolutely landmark work at UCSB with Matthew Fisher. He then went on to Caltech as a postdoc. Now he's at Princeton, right? And he's carrying those methods with him as he goes using them in all of his studies, right? And so this educational impact is tremendous, even if this code takes a long time to compile and is unwieldy, okay? So where are we now? I told you about SourceForge. You can go and check this out. We have a GitHub echo of this. And you know, this works pretty well, 3,000 users, right? I mean, that's not, or 3,000 downloads, about 100 verified groups or individuals that use this code that we know of personally, so a significant user base. But I would say, you know, for the most part, it's still my group doing most of this. We have a few other people participating, but not too many yet. Okay, so where are we going? Well, and I know this might be language that seems a little strange to some people in this audience, but I've actually come to love this language, even though it's very sort of cynical at first. So joining this, you know, the cyberinfrastructure software ecosystem, as they would call it, the great thing about being part of this NSF program, so I'm part of what was called the SI2, SSI, SSE program, and it's now being called the Cyberinfrastructure for Sustained Scientific Innovation, or CSSI program. Being part of that has allowed me to go to these conferences where, you know, I am getting access to 80 people in cyber infrastructure who teach me all new ideas about how I can package my code, the whole thing with Docker that I'm doing GUIs properly, all of that, you know, the kind of stuff that Garrett was talking about, right? Like those kinds of things would be just normal for them. That'd just be starting, and they go from there. Yeah. Yeah. I'm wrapping up. Yeah, just a few slides on different. Okay, thanks a lot. And so as part of that, you can join the Science Gateways Community Institute, and they provide a quarter-time person who will work with you for 6 months, extendable to a year, to build a science gateway. We're doing that now. And they have these boot camps where they educate your students on how to make sustainable software. So you guys talked about what they would call the Valley of Death, you know, where you create this beautiful package and then people want to use it out here, but there's this maintenance valley in between. And they talk about how to get past that, and they have really definite plans for it. So I think you might like to participate with them, even if you're not going to put in one of these NSF grants. So we talked about MolSSI. This is the other one. It was suggested right in the NSF paperwork, by the way, so it's not like it's, you know, an unusual thing to talk about. And again, you know, that there's a significant educational piece to this. It's kind of just getting started, but I think it's got some great opportunities, and it is a lot of resources. Maybe some people in this group might want to be a part of that. Now, the example that they gave at NSF, and I spent some time on, is Nanohub. So, you know, Hussein had asked me for a demo. I mean, there's 400 tools, 1.4 million users. It's a tremendous number of things you can do with it. It's incredibly useful, and it's just really point and click. And And so, when you enter, it starts with your carbon nanotube here, and then you hit the menu button up here, and here's what you see. You see that there are all these different resources, okay? And some things you can download and use offline, other things you use through the site as a science gateway. As you continue to go through exploring, you'll see that, there's really quite a lot of people interacting on this site. And I think most importantly, somehow, they have this Nanohub U, which is a bunch of courses that will really teach you nanophysics, right? So, like at my university, we have a few people in nanophysics, but we don't have, 50, right? Here you have access to all of these great classes. So I want to point out that this is common to MUL-SSI, it's common to Nanohub, and it's common to ALPS, actually, this educational component. So in conclusion, I've told you about QuSP, which is a quantum simulation package that provides a robust and flexible integrated modeling environment for entangled quantum dynamics. I specifically focused on molecular Hubbard Hamiltonian because it was so relevant to this audience, and I gave you a couple of sets of results just in a slide or so of things that have come out of this code in my own group. The real bottleneck is that quantum simulators really involve a multi-scale and multi-field approach, right, to making them work. Yeah, and that's what a code group can do. So this group, in my mind, has a few options. It's possible to go to NSF and apply for one of these SSIs or framework, whatever you want to call them now. You can build a science gateway with Science Gateways Community Institute. You don't have to have an NSF grant for them to work with you. I mean, they're happy to just work with you. And then you can work with MUL-SSI, or you can try to build your own copy of something like that. You have to decide what's more cost-effective and time-effective, right? There's a big staff that runs that. But whatever we do, I think this education piece is the key piece. So not only in ALPS, but if you go, I just put the website there for you to have a look. If you go to PhET, right, that's a website where you can learn quantum mechanics by playing with apps, just like Garrett showed, through, I think it's Java. And it really, I really don't think any kind of group can be successful without that piece. If you just put your codes up all together and there's no education piece, you really won't go anywhere. And you see Nanohub and ALPS and all of them, they all have a major education piece. And NSF supports that kind of thing. So anyway, I'm going to end there. Thank you.